and welcome to today's lecture. Today we will take our first step into the world of modern algebraic geometry and study schemes rather than varieties. So why do we want to do this? And what is this all about? So far we've been looking at algebraic varieties. Algebraic varieties we have considered over an algebraically closed field. So once we start with an algebraic variety, then we are stuck with our algebraically closed field, and all the functions, the regular functions on this variety, go into this field. We have also considered finitely generated stuff without nilpotents. So remember that an algebraic variety is glued together from affine varieties, and the coordinate algebras of affine varieties, these are finitely generated algebras without nilpotents. For example, we haven't been able to look at things like the polynomial ring in one variable quotiented by the ideal generated by t squared, even though this is useful, for example, in the construction of tangent and cotangent spaces. And thirdly, we have only looked at such varieties that have closed points. So in the Zariski topology, on varieties, points are closed. So all points are somehow created equal in this notion, and that is a bit restrictive. With schemes, we will eliminate the need of a base field at all, meaning that we can work with a scheme just in an absolute sense, not over anything, or if we wish, over a field, closed or not, or an arbitrary commutative ring, or even over a different scheme as we go by. Also, the framework in general will be broad and robust. So the example I showed just now showed you that if we take something as innocent as the quotient ring of a ring without nilpotents, we might end up with a ring with nilpotents. So the framework of varieties is not robust. We can get out of it rather easily. Schemes will provide a more broad and robust framework. And it will therefore have better algebraic or functorial properties. And we can embed schemes into an even larger category of functors. And this will give us more algebraic tools and less of a need to think about specific geometric situations. So what is a scheme? Well, what we will do is we will define what schemes are in this lecture. And what a scheme is it's three things. It's going to be a set with a topology and a structure sheaf. So that is roughly as with algebraic varieties. We will have to define these things one by one. And we will also define the notion of affine scheme to start with, and then schemes will be objects that are glued together from these affine schemes. And everything works in analogy to what we did with algebraic varieties. So let us get started. Let's start by defining what an affine scheme is. And so let's start by looking at the underlying set of an affine scheme. As always, we denote by R a unital commutative ring. So the affine scheme associated to R, also known as the spectrum of R, or the prime spectrum of R, is the set Spec R of all prime ideals of R. So we've dealt with maximal spectra before, where we have looked at only the maximal ideals. Now we look at all prime ideals. And note that R now is a general unital commutative ring. It is not assumed to be an algebra over some fixed field. It is just a ring. So what examples do we have? Well, rings have so far arisen for us as coordinate rings of affine varieties, denoted OX of X, or sometimes in the literature K bracket X, where X is an affine variety over some algebraically closed field. So if we take such a ring and consider all the prime ideals, we're considering more than the points of the variety itself. So Spec R, the prime spectrum of R, is called the affine scheme associated to the variety X. And in terms of points, so as sets, we have seen that X can be identified with the sets of maximal ideals. So a point, say, if we embed this into n space, a point A1, An will correspond to the maximal ideal generated by x1 minus A1, and so on. But now we consider all the prime ideals. So what does this contain? Well, roughly speaking, as a set, Spec R contains the points, the set of all points, but also the set of all irreducible subvarieties. Because the ideal of a point is a maximal ideal, but the ideal, the vanishing ideal of any irreducible subvariety is a prime ideal. So we're considering such things as well as points in our scheme. For example, we can take the polynomial ring in one variable. So here t is a variable. So we're still working over an algebraically closed field in this example. And so we have the maximal ideals. And these are of the form t minus lambda, where lambda is an element in the field. But we also have the prime non-maximal ideal, which is the ideal 0. So that is what is added. And in terms of varieties, so k of t is the coordinate ring of the affine line. So here we have the points of the affine line as a variety. They are points of our scheme. And also the prime ideal 0, which corresponds to the whole variety because it's irreducible, is also a point in our scheme. A much more innocent, or perhaps much more powerful, depending on how you view it, ring is the ring of all integers. So here Spec Z, well, of course, this is the set of ideals generated by prime numbers, and the 0 ideal, in analogy to the previous situation. The 0 ideal is prime, but not maximal. So now we have defined the set underlying scheme, and we want to start thinking about functions and zero loci and all that, and towards defining some sort of vanishing sets to define some topology. So what does a function on a scheme mean? Well, what should it be? Remember when we had affine varieties, our functions were the functions from the variety itself to the underlying field. But now we do not have any underlying field, so we need to do this more carefully. What we note, because we want to work analogously to the variety case, is that if you take any maximal ideal, so any element of the maximal spectrum of R, the field K, this was a consequence of Noether normalization, the field K can be seen as the quotient of the ring R, whose spectrum you're considering, by the maximal ideal. Also, the global functions on X, so here we have X equals M spec of R, consist of the elements of the ring itself. This was this duality between rings and varieties. So we might want to do the same thing here. We might want to identify as our field to which the functions will send elements such quotient rings. But now our ideals are not maximal, they are prime, so we need to take fields of fractions. So let now X be the prime spectrum, the spectrum of R, and take a point in X. So P is a prime ideal in the ring R. Then the residue field, K of P, or kappa of P, as we denote it here, of the affine scheme X at the point P is the field of fractions of R mod P. So because P is prime, this is an integral domain, and so it makes sense to define its field of fractions. And now we want to view points of R as global functions. So given an element of R, we want to evaluate f at a point P of the scheme. So we want to say what it means that something is the value of f at a prime ideal P. So starting with f, we just map it to its class in R mod P and then include it in the field of fraction. And so this will be thought of as the value of f at P. So, for example, if we are looking at R, the coordinate ring of an affine variety, so here X is an affine variety over some algebraically closed field, okay, then the residue field of P, this is going to be just K if P is maximal, or it is going to be the field of rational functions on Y if P is the ideal of Y with Y irreducible. So what does it mean to evaluate an element of R at P? Well, the element of R now, these are global functions on the affine variety X. So evaluating such a function at a maximal ideal will be the image of, so this is viewed as R mod P, so it's the image of f under this quotient projection. But if you pause and think, that is exactly the actual value of f at the actual point P of the variety corresponding to this maximal ideal. So there nothing new is happening. But now we have something much more exotic if we evaluate an element of the ring as at an irreducible variety. So this will be the rational function on this irreducible variety that is induced by the global function f. So this is something much more complex, much bigger. A more quaint example is that of the integers. So remember now the prime ideals are the ideal generated by prime numbers and the ideal 0. So what does f of P mean? Well, for example, we can take f as the integer 7 and P as the ideal generated by 5. Then f of P is just 7 of 5, which looks very strange, but this is the element 2 in the ring Z, in the field Z mod 5 Z. So this is the evaluation of the number 7 modulo the ideal 5, 7 mod 5. So equipped with this, we can define something akin to the 0 locus of a set of elements in the ring. You might want to pause and think about the definition in the variety case. But now we consider a ring R and the affine scheme associated to R, and take any subset of R we should view this as a subset of functions. So the zero set should just naively be the set of all points in the scheme, points now understood as prime ideals, where f vanishes, such that the function f in S, for any function f in S, f of p is equal to 0. Now, f, by the definition of evaluation at p, this means that f mod p is 0, so that f is congruent to 0 mod p, or in other words, that f belongs to p. This is what it means that f of p is equal to 0. So really, the set of all prime ideals where all points of S vanish, these are all the prime ideals containing the set X. So this is a more succinct way to write down this zero set. Then, going in the opposite direction, we want to define the ideal of a set of a scheme. So again, pause and think about how this was done in the variety case. So we want to take now a subset of X, where X is the set of all prime ideals of R. And again, naively, we want the ideal of this subset to be the set of all functions that vanish on all points of this set Y. And this indeed works, and because this means that you want F to belong to P, you can think of how to write this in a short way. Well, this is exactly the intersection of all prime ideals that belong to the set Y. So, for example, if the ring R is the ring of the integers and Y is the set consisting of the 2 points ideal generated by 2 and ideal generated by 3, well, then the ideal corresponding to Y, this is the ideal generated by 6. Because for an integer to be 0 mod 2 and mod 3, it has to be 0 mod 6. And note that I of Y is an ideal indeed, but not in general a prime ideal. And as for varieties, you get a version of the Nullstellensatz for schemes. So these two maps are mutually inverse, inclusion reversing bijections between the zero loci of X and the radical ideals of R. So again, we have V of I of Y, this is Y, and I of V of J, this is the radical of J. Proving this is very analogous to the proof of the Nullstellensatz for affine varieties that you have already proved. The only thing you need is the fact that the intersection of all prime ideals containing a certain ideal J is exactly the radical of J. This is a fact from commutative algebra that lies behind this thing. So as for varieties also, the empty set is the vanishing set of the whole ring. The scheme X entirely is the vanishing set of the zero element. And you can show that the union of two vanishing sets is a vanishing set. The union of two zero loci is a zero locus, and therefore any finite union of zero loci is a zero locus. Also, any intersection, finite or infinite, of zero loci is a zero locus. All of this is analogous to the case for varieties, and therefore they define a topology, and this is called the Zariski topology on X. So it is the topology now not only on the set of all maximal ideals of R, but on the set of all prime ideals of R, So the topology defined by the closed sets being exactly the sets V of S with S in R. And these sets V of S, they behave exactly as for varieties, meaning that, for example, if you have an ideal generated by a set S, then V of J is the same as V of S, and so on. And then you can show that there is a concrete base or basis of this topology. And exactly as in the variety case, this is the collection of all principal open subsets. So sets except for the vanishing set of one element F in R, or in other words, the set of all prime ideals not containing F. And remember, as usual, I'm using the convention that I write V of F instead of V of the set of F. To show that this is a base, what you need to show is that these cover the whole space, but this you get by taking F equals 1. And also that the intersection of two such things is principal open, or I mean contains a principal open subset, but in fact it is principal open. Thanks to the fact that our ideals are prime, you can show this exactly as you would do for the maximal ideal case. So now on our affine schemes, X equal spec R, we have a topology, and so we have made them into topological spaces. One very important point about this is that not all points are closed. So a point P in X is closed if and only if P is a maximal ideal. Why is that? Well, that is because if you take a point P and consider the closure of the set containing P in the Zariski topology, if P is closed, this should give you just P. But instead, this is in general V of P, which by the previous definition is the set of all P prime in spec R that contain P. So if P is not maximal, then the closure will be the set of all maximal ideals containing P. I mean, this is true also if P is maximal, but if P is not maximal, this will certainly not be the set of P itself. So this is equal to P if and only if P is maximal. So for example, if we have the scheme associated to the variety, say, X, then we have the closed points. These are the actual points of the variety, and the non-closed points, called the generic points, and the generic points are the irreducible subvarieties, or rather the prime ideals corresponding to irreducible subvarieties. Another example is if we take R equals the integers, then we have the points P with P a prime number. They are closed, but the point 0 is generic. And one way to maybe understand this terminology is that if I have an integer f, then evaluating it at the prime P gives me f mod P. But evaluating at 0, now the field of fraction of z mod 0, this is the field of fraction of z, which is the rational numbers. So this is, get f as a rational number. So I have not evaluated it at a specific point, rather I have looked at f generically somehow. Or in the case of varieties, I am evaluating a function on a generic point as an element of the field of fractions or field of rational functions on an irreducible subset. So this is somehow something that's defined generically on the variety.